The man who worked out how often the Cascadia subduction zone produces catastrophic earthquakes has now said in print that Cascadia is not the worst-case scenario. His name is Chris Goldfinger. He is a marine geologist at Oregon State University, and the reason that sentence carries weight is that he is one of the people who established the Cascadia earthquake record in the first place. Nobody would call him an alarmist in reverse. The man who built the record is telling us the record is incomplete. What he means is this: we have spent decades treating the big one as a single event on a single fault. The evidence now points somewhere else. It points to Cascadia rupturing and then the San Andreas rupturing after it at its northern end, minutes to hours later, in the same sequence. Not two earthquakes in the same decade, two earthquakes in the same afternoon on two different fault systems covering the coastline from Seattle to San Francisco. And the evidence for it came out of the seafloor by accident, because in 1999, a research ship got lost. Start with the accident, because the whole thing hangs on it. In 1999, Goldfinger was at sea off the coast of Oregon and Northern California, doing what he had already been doing for years, pulling long tubes of mud out of the seafloor to read the earthquake history of the subduction zone offshore. A navigational error put the ship in the wrong place. By the time anyone noticed, they were about 55 miles south of Cape Mendocino, which is well outside the Cascadia zone and inside the San Andreas Fault zone instead. The sensible thing at that point is to correct course and go back. Instead, they decided that since the ship was already there and the equipment was already rigged, they might as well take a core. It's worth saying what taking a core involves, because it's not delicate work. A steel tube several meters long is driven down into the sea floor from a ship, thousands of feet above, and pulled back up full of mud in the order it was deposited. Do it right, and you have brought a few thousand years of history onto the deck in one piece. Do it wrong, and you have a tube of stirred sediment that tells you nothing. What came up did not make sense. And it did not make sense for 25 years. The paper explaining it was published this year. To understand what was wrong with that core, you need to know what these people are actually reading, and it is one of the more elegant ideas in geology. When a large earthquake shakes the seafloor, sediment that has been sitting on underwater slopes comes loose. It slides downhill as an underwater avalanche, a dense cloud of mud and sand pouring down submarine canyons, and eventually it settles out on the deep ocean floor. Now the elegant part. As that cloud settles, it sorts itself. The heaviest grains fall out first, so coarse sand lands at the bottom. Finer particles stay suspended longer and settle on top. Fine over coarse every single time, because that is what gravity does to a mixture of particles sizes in water. A layer like that is called a turbidite, and it is effectively a receipt. One earthquake, one layer, filled in order, with the oldest at the bottom and the newest at the top, undisturbed for thousands of years. Drill down through the seafloor and you're reading a stack of receipts. Count the layers and you know how many big earthquakes there have been. Date them and you know when. That method is how the Cascadia earthquake record was built in the first place, and it is why we know that the last full rupture there was in January of 1700. And the method has a check built into it, which is the part that makes it trustworthy. There are earthquakes on the coast that we know about from written records, and the biggest of them is San Francisco in 1906. When you drill into the seafloor just south of the Junction, 1906 is there. A thin bed of sediment in the right place in the stack at the right depth for its age. So the technique is not being asked to be believed on faith. It reproduces an earthquake that people photographed. So the rule is simple: coarse at the bottom, fine on top. In the core from the wrong place, and then in others, the sequence was inverted. Fine, silty sediment at the bottom, and above it, coarse sand. That should not be possible from a single event. Sorting does not run backwards. A single avalanche cannot leave its heavy grains at the top. In Goldfinger's own description of it, they found these big, thick, sandy events with a fine-grained element and a very coarse-grained sandy unit sitting above it, and they were scratching their heads. There's only one straightforward way to get that arrangement. It's not one avalanche, it's two. The first event deposits a normal layer. Then, before the fine sediment above it has had time to consolidate, a second avalanche arrives and dumps its coarse material straight over the lot. Two receipts stacked so close together that they look like one strange one. And the two layers have to arrive close together for this to work at all. Fine sediment settling out of water does not stay loose for long. Give it years and it compacts, and a later avalanche landing on top of it produces two clearly separate beds with a boundary between them, which is exactly what the record normally looks like. To get the arrangement they were seeing, the second event has to arrive while the first deposit is still soft. They called these doublets, and the question stopped being what they are and became what could possibly produce two of them that close together in the same place. The location matters, and it is the least known important place in North America. Cape Mendocino is on the northern California coast, and just offshore is a point where three tectonic plates meet. Geologists call it a triple junction. It is also the place where the Cascadia subduction zone ends and the northern San Andreas begins. These are not two faults that happen to be in the same region. They are joined. The southern end is one of the northern end of the other, and the boundary between them sits under the water off that cape. Which means that if there is anywhere on Earth where an earthquake on one system could reach across and set off the other, it's there. A triple junction is not a place where three faults cross. It is a place where three tectonic plates meet at a point. And off Cape Mendocino, those three plates are the Pacific Plate, the North American Plate, and a small one called the Gorda Plate. Each pair of them has a different kind of boundary, which is why the geology changes character within a few tens of miles of that spot, and why that stretch of coast has more earthquakes than anywhere else in California. It also means the seafloor at that spot is the only place where a single core can record both. Sediment from a Cascadia rupture and sediment from a San Andreas rupture arrive in the same canyons and stack in the same order they happened. The ship that got lost in 1999 got lost in the one place where the question could be answered. What they did next is the part that turns a strange sample into an argument, and it changes what the big one means for the entire West Coast. Subscribe and stay with me. Before the sediment, there is a smaller version of this that we watched happen. On the morning of the 25th of April 1992, a magnitude 7.2 earthquake struck offshore near the town of Petrolia at the southern end of that subduction zone, a few miles from Cape Mendocino. It lifted the coastline. It generated a tsunami, and it produced the strongest ground accelerations ever recorded in a California earthquake. At Cape Mendocino, the instrument measured a vertical acceleration close to twice the force of gravity, which means that for a fraction of a second, loose objects on the ground were not falling back down. That's not the interesting part. The interesting part happened the next day. Two more large earthquakes, magnitude 6.5 and 6.6, offshore about 19 miles west of the first one. And they were not aftershocks in the ordinary sense. They occurred on different faults inside a different tectonic plate, the Gorda Plate, oriented in a different direction from the main shock. One earthquake on one system, followed within hours by earthquakes on a separate system at the same junction, recorded by seismometers in living memory, with the ground movement measured afterwards by survey. The U.S. Geological Survey found 12 benchmarks within 60 miles of the epicenter had physically moved, some by up to 16 inches sideways. That is the behavior the sediment cores are describing at a much smaller scale with instruments instead of mud. And it is not a rare event for that stretch of coast. The region around Cape Mendocino accounts for roughly a quarter of all the seismic energy released in California, and it has produced more than 60 damaging earthquakes since the middle of the 19th century. It is the most seismically active place in the state, and almost nobody outside Northern California has heard of it. A strange layer in one core is an anomaly. To make it an argument, you need three things: more of them, dates, and a reason to rule out the boring explanations. The team went back for cores covering roughly 3,100 years of history, from sites both north and south of Cape Mendocino, which is to say from the Cascadia side and from the San Andreas side. The doublets kept appearing, and when they radiocarbon dated the layers, the The paired deposits from opposite sides of the junction turned out to have formed at roughly the same time within the precision that dating allows. Now the boring explanations, because this is where a claim like this normally dies. The obvious one is aftershocks. A big earthquake is followed by smaller ones, and a large aftershock could trigger a second avalanche. But an aftershock of the Cascadia earthquake would be recorded on the Cascadia side, and it would not put a San Andreas signature into a core 50 miles south of the junction. The pattern is the wrong shape for aftershocks. The other is coincidence. Two unrelated earthquakes that happen to occur close in time. That works for one doublet. It does not work for a series of them repeating across 3,000 years, always in pairs, always with the same order. Which leaves the conclusion the paper draws. A large Cascadia rupture followed minutes to hours later by movement at the northern edge of its neighbor. Here is why the timing is the whole story and not a detail. If Cascadia and the San Andreas rupture years apart, they are two disasters. Bad, but sequential. The first one is responded to, and the second one happens to a region that has already learned something. If they rupture the same afternoon, they are one disaster and it behaves completely differently. Emergency response works by moving resources from the places that are fine to the places that are not. Aircraft, crews, equipment, hospital capacity, all of it flows in from outside the affected area. That logic assumes there is an outside. A Cascadia rupture damages the coast from British Columbia to Northern California. A northern San Andreas rupture reaches the San Francisco Bay Area. Put them in the same afternoon, and the entire west coast of the United States is inside the affected area at once, and the nearest undamaged staging ground is a long way east, on the far side of mountain ranges with roads and ports in between in unknown condition. There is also the tsunami. A rupture out there generates one, and the coastline it hits includes towns that would in any other scenario be part of the response rather than part of the emergency. The planning documents for the Pacific Northwest are built around a Cascadia event. They're not built around a Cascadia event plus a San Andreas event on the same day. Now the part that most coverage of this study did not include. This is evidence of a pattern in the past. It's not a prediction. It's not a warning, and nothing in it says the next Cascadia rupture will behave the same way. The evidence itself has real limits, and they are worth stating plainly. Radiocarbon dating of seafloor sediment gives you a window, not a date. When the paper says two events happen at roughly the same time, the precision behind that phrase is measured in decades, not in hours. The minutes to hours interpretation comes from the physical structure of the layers, from the fact that the second avalanche arrived before the first had settled, and not from the dating. That is a reasonable inference. It's not a measurement, and the authors are careful about the difference. There is an older dispute in the background that a viewer should know about. Reading earthquake history out of turbidites has been questioned before. In 2024, a separate study raised questions about how reliably the Cascadia record can be reconstructed from these layers, arguing that not every turbidite necessarily corresponds to an earthquake. That debate is not settled, and this paper sits inside of it rather than above it. So the honest summary is narrower than the headlines were. Something in the sediment record repeatedly looks like two large earthquakes in quick succession at the junction of these two systems. The best available explanation is that the faults have sometimes triggered each other. Whether they will do it next time is unknown and unknowable with current methods. So what would close the question? More cores from places along the junction is the obvious answer and the one being worked on. Every additional site either keeps producing paired layers or stops producing them, and either result is informative. Better dating precision would help, although the limits there are physical rather than a matter of effort. Radiocarbon does what radiocarbon does. And offshore evidence matters. If a Cascadia rupture really did set off its southern neighbor repeatedly, there should be traces of it on land as well. Trenches dug across that fault containing ruptures that date to the same windows as known Cascadia events. Those trenches are being dug. None of that gives anyone a date. What it changes is what gets planned for, and that is a decision made years in advance about an event with no schedule. Go back to the ship for a moment. In 1999, a navigational error put a research vessel in the wrong stretch of ocean. Somebody made the small, unglamorous decision to take a sample anyway, since they were already there. What came up was a stack of receipts filed in the wrong order, and nobody could explain it for 25 years. That is what most discoveries actually look like from the inside. Not a moment of insight, but an anomaly that will not go away, sitting in a freezer in Oregon until somebody collects enough of them to see the shape. The shape, in this case, is that the two most dangerous fault systems in the western United States may not be two problems. They may be one with a joint in the middle. And if the second half of that pair is the one you want to understand, the San Andreas has a problem of its own that has nothing to do with Cascadia. There is one specific gap in the mountains where the last great rupture came to a halt, and whether the next one stops in the same place decides how large it gets. We made a whole video on it. Start there.